have different fabrication techniques to fabricate nanomaterials. Okay. So probably I think today we planned for fabricating some kind of a nanomaterials and nanocomposites and composites. But the schedule is slightly changed, so we are planning it tomorrow. So I'll have a 2 hours lecture and then the professor will come and then he has a tutorial one lecture today. So in this particular thing, today I'll explain how to fabricate a composite and tomorrow we'll fabricate that. 1 or 2 composites. My students will help you, like they'll fabricate few samples and you can see it, you can see the fabrication techniques and what basic techniques, what things we'll adopt. Like we started this particular fabrication. Earlier there are the different kind of concepts we have. There are filament winding, bulk fusion technique, vacuum bagging technique. There are different techniques to fabricate it. So we need to adopt a basic technique where we can fabricate a material easily. Okay. So the traditional technique is a hand lay technique. In the name itself, like a hand lay up, means using our hands we lay the material and then fabricate it. That's what is our name called a hand lay technique. Okay. So what we prepare is we prepare a mold. Once we prepare a mold, then we go for calculations. We calculate it because we need to fabricate a plate. If I want to fabricate a plate, then we need total volume of the plate. I need to calculate total volume of the plate. In the total volume of composite, we are adding 2 terms. One is matrix, another one is a reinforcement. So the equation gives you like volume of composite equals to volume of matrix plus volume of reinforcement. So the total volume of a composite consists of a matrix as well as reinforcement. 2 terms will be there. So in these 2 terms, how much amount of matrix to be added, how much amount of reinforcements to be added, that comes a designing part of a material. So always we need to design our own materials. For example, if I want to design a material which having a higher strength, then I select a higher reinforcements. If I want to design a material with a minimum strength, but I need a basic full protection of matrix, then I go for a higher matrix. Okay. So coming to this, before that, I'll ask you one more question. For example, if I want to make a sugar juice, how much sugar spoons we will add it in a 1 liter of water? Again, it depends upon the person to person varies. Assuming that we will add a 1 or 2 spoons or 3 spoons of sugar. If I add a half kg of sugar, in 1 liter of water, then what happens? Sugar juice will form or not? No. Why it won't form? Saturation will be done. Means, are we adding a water to sugar or sugar to water? Sugar to water. In a sugar we are adding a water. Again it forms something. Let us assume 1 kg of sugar, 1 liter of water. Sugar remains like a crystals. Water is added to it. Water will be absorbed and then crystals will be visible. Half kg still, but mixed with the water, some kind of waterish kind of thing will be. Then what best combination will can? In a 1 liter of water, add a 3 spoons of sugar, it's perfect. More sugar means not possible. Saturation is coming. So in the designing of matrix and reinforcement, there may be a saturation point. That saturation point gives you how much amount of matrix to be added, how much amount of reinforcements to be added. So in that particular thing, for example, if I am making not a sugar juice, lemon sugar juice. Okay? Lemon sugar juice. Then how much of lemon we'll add? Lemon is a water, right? We can add 4 or 5 lemons. What happens? If I add 4 or 5 lemons, make this thing and add to the water, can we drink? We can drink. What happens? It will be a more like citric kind of thing, right? So which we can't take. Because if we add more material which is having the same properties, that also we can't take. Here the liquid sugar saturation is there. The other material which is in a liquid state, if we add more also we are not taking it. The same concept applicable in the designing of composites. Whenever we are selecting a material, reinforcement will select, in that matrix we are going to add, that matrix will be very high as like water. The sugar which we are going to add 2-3 spoons, that remains like a reinforcement. Reinforcement gives you strength. We can add 60-70% of a reinforcements and then 30% of a matrix, which won't wet the material, because that much high amount of reinforcements never wet or make a structure with the lower amount of matrix. So when you are designing it, we need to see matrix will be higher, reinforcements to be lower. Hybridization means the new material which we said, that will be a limited level. So when we talk about, later comes to the composites, nanocomposites, I'll tell that what combinations, what things right now research are going on, and what we are trying, what we are doing, that I'll explain. So this is hand lab technique. So as we are preparing a sugar juice, these composites are similar, because many people say like when we are doing a research, always there is a point like you are doing like research like making a juice. Means one material modified with another material, either banana juice, pineapple juice, juice will vary, right? Composite also similar like that. In epoxy matrix, put L2O3 epoxy composites. Put the same thing, instead of Al2O3 SiC composites. Combine Al2O3 SiC, SiC3 Al2O3 composites. So it's like a juice. You add new material, new juice will come. But the thing is whether it is having an application or not, whether what kind of material it is, that comes after once you prepare the material. Okay. Let us talk later, come to that. This is a hand lab technique. The same thing. The another technique is a filament binding. This particular filament binding, you can see like how many of you heard about Indian missiles? Have you heard about any Indian missiles? What kind of rockets, missiles we have for fighting with other countries? Agni, BrahMos. Okay. If it is Agni, BrahMos, like for example Agni 1, how much distance it will travel? We know Agnis, BrahMos, how much distance it will travel, that we don't know. It will be very big, right? Not a small one. It's a very big one. That is at least you know that. Then you tell me like how much distance it will travel. Agni 1 travels 500 kilometers hardly. Then if I want to fight, I don't name a country which will be controversy, like okay, any country something XYZ. Okay? So I want to put a bomb on XYZ country. So if I put from Hyderabad, from DRDO office, then where it will fall? 500 kilometers means it will go on far on Nagpur. Correct? It's a 500 kilometers in Nagpur, right? From Hyderabad. So if I put it here, it will fall on Nagpur. If I want to put that same thing to some other country means I will go to border and take all the things and then put that missile from the border. I develop in Hyderabad, transport it to the border. From the border I will put that missile. Okay? That is for Agni 1. What exactly in the Agni 1 happens is, the entire Agni 1 is cased with metals. The entire material is developed with the materials, with the metal materials. Agni 2, 1000 kilometers. Agni 3, Agni 4, now it is around 3000, 5000 kilometers. It's an intercontinental missile. So means sitting in Hyderabad we can switch on and then we'll hit some other continent. Okay? So that's the point. Like nowadays, these concepts what we have, if you see the US and other countries, they have almost 30-40 years back. Okay? That's why we purchase everything from there. Nowadays we are studying about composites. Many are seriously listening about composites. I started 15 years back. You are now studying it. Okay? After 15 years also we will study this. But the other countries, they start studying about it because they are recycled it already. When I started, they are in the recycle stage. All the US, Europe, Israel, all those, they are recycling the composites. Means develop, used, recycle. We are in the developing stage. Now they are developing functional graded materials. So in the class 90% of the people don't know about functional graded materials. They are developing it. So we will develop that after 10 years. Okay. So start learning the new things. Why I always say like in a classes means, but sir what you are doing, like why don't you develop? So we are developing it, but it depends upon the people, right? If people don't know, if I say FGM, if they don't know about the word, then I always say something which is not going to our minds. So So first people has to know about the new materials, new concepts, new technologies. Always exactly what the research is going on. Some X material prepared one kind of a juice. I'll change the fruit, make a new juice. Or else I'll combine the two fruits, make a hybrid juice. This is what going on the research. Okay. Still I am also doing the same thing, I am not pointing to someone else. But the limitations we are doing it, if we know the new things, new materials, new concepts, then we can develop new things. Only thing is, if you don't know the terms, don't try it. First, at least knowing the terms is first important. If we know the terms, okay, we will start thinking about it. Okay. So my topic is about like not exactly about nanomaterials and not about the concept. My concept is about like at least know new materials. Somebody asks, okay, I know that. I know this material. For example, almost 2 months or like 1 year back, I don't know ChatGPT. When you're telling that, then I feel like I don't know about ChatGPT. Now I learned ChatGPT. I'm amazing, develops, and all those things I'm doing it. Okay. Still, many people don't know about it. And DeepSeek and other terms, new terms are coming, right? So we need to upgrade ourselves. If we don't upgrade ourselves, then we are out. Okay. So nowadays many things are going up, right? We need to upgrade. Like materials, every day we need to upgrade ourselves. New materials are going to come. If you don't upgrade yourself, if you are stick with the same old materials, it won't work. So this is a filament binding in Agni. As start there like Agni missiles, they use this particular filament binding technique to develop all the DRDO labs. They use a filament binding technique to develop a composite casings. All the composite casings they develop with this, and then it will be a carbon fibers. So the casings they develop, 3 motors will be there, 3 casings, 1, 2, 3, because the fuel will be very less to transport a 5,000 kilometers in a small tank. You don't fill the continuously, like for example, missile is going, we'll send a one more filling missile in the back, it will fill the fuel, it won't like that, right? Once it starts to go, that's it. So there will be a 3 casings. So one casing will comes at some location, after another casing, finally bomb will go and fall on the 5,000 kilometers. So that's what the concept in the missiles. So they use this particular technique. The filament binding is an old one, old image. And vacuum bagging technique. Now the question is, yes, we have seen different techniques, right? 3 different techniques we have seen. There are more techniques. What is the need of like once we have one technique, one manufacturing technique, probably I think if it's a nanomaterials, if I say, you might have seen yesterday some manufacturing technique, soul gel method, right? You have seen soul gel method. Again, that is modified to some other technique. Once we have the ball milling method, why need our soul gel method? Once we have a soul gel method, why auto combustion or soul gel kind of advanced methods? So what is the need of it actually? Why we are going for the higher techniques? So every manufacturing technique have certain disadvantage. Won't gives you a better material. When you fabricate a nanomaterial, nanocomposite or a composite, any kind of a fabrications, there will be certain defects in the fabrication techniques. To address that, we modify the technique. In the very first one I said, this one we'll do in a normal atmosphere. In a normal atmosphere we're doing it. Then what happens exactly? We are mixing the material in a normal atmosphere, combining 2 materials, bubbles will be formed. That bubbles, if you keep it in an atmosphere for a longer time also it won't come out, because the bubble formation will be very high, won't come out. If I directly pour into a mold, then it will saturate and it will fix inside it, it forms a voids. When there is a voids, at the fabrication stage itself I have a defect. Then when there is a defect, then there is no point like we have a better material. So to avoid that, we go for a vacuum, keeping that entire in the vacuum bag to remove that bubbles, air bubbles. That's called vacuum bagging technique, filament binding technique, pultrusion technique, hand layer technique, spray up technique. So there are further techniques are modified with these things. Okay. So with these terms, like before going to nano fabrications, I think already you have seen it. So we'll have a small break. There are different terms. I don't want again go to this because earlier professor already talked about it. Just for only two techniques what I developed when I am doing my PhD. I'll just talk about that. So one is a ball milling. When I done my BTech PhD in 2011, so I used that. So I just talk about that particular terms, that ball milling and then auto combustion process, where we can develop alumina Al2O3 with a low cost, we can say, low size materials. We can fabricate on a lab. What I have done in my PhD, that I'll talk for 15 to 20 minutes. That's the next one. And these other terms are like top-down approach, bottom approach. I think already discussed, right? Earlier classes, I think already done. What's the top-down, bottom-up approach? All this. That's keep all those. So this process I'll discuss. Other these two things. After that, we'll talk about characterizations. So how to characterize it. So what are the steps involved in it? How to understand the material? Because as of we have just seen the composites, nanocomposites, different materials. To understand in the next level, we need to characterize it. So after a break, we'll see those things. Okay. So quickly, like right now it's 3:40. So we'll have a break for 10 minutes. So up to 3:40, 3:50 we'll have a break, and we'll assemble by 3:50. We'll start the break. Yeah. Thank you. Before this, we have seen some publications related to nanomaterials, nanocomposites, and composites. Now, just characterization about the materials, characterization of composites, nanocomposites. So to understand any kind of a material, first we need to characterize it. We need to understand test the material and then see the properties. Once we see the properties, then we understand the material in a better way. So coming to characterizations, mechanically we have tensile and compression. Tensile means apply the load of opposite side. If you pull the material, so in opposite direction, so how the elongations will happen. If it is having a continuous fiber, discontinuous fiber, random fiber, different kind of fibers or particles, how it will stretch, how it will fracture. So all those things will come study in the tensile test. Next one is the compression. Compression will be in opposite direction. We'll compress that. Once we are compressing it, then how the load is observing, and after that, once the load is observed, and finally how the fracture happens. Those two things will come under compression. Normally in a tension, when you are applying a load, the fibers will stretch. When you talk about, like, as topic is about nano, so I talk the level in terms of micro level and nano level studies. When you study any kind of a material or a subject or any concept, there is macro studies, micro studies, nano studies. Macro studies means outer level. Like just see the material, fracture it, break it, see that how it is breaking, whether brittle or ductile. Micro level means understanding the deformations, how the material is elongating, how the material is stretching, and finally how the fracture is happening. Coming to the nano level, it about the atoms, how atoms are dislocating, how atoms are moving, how atoms are stretching. So in this particular thing, so we have a plastic deformation and elastic deformation. Any material, whether it is a ductile or a brittle material, so we have a elastic deformation and plastic deformation. Basically in a brittle materials we don't see any plastic deformation. Means more elongation with a load. We have a failure at one point, a maximum amount of load is observed, fracture at one point. That is what we see in the brittle materials. When it comes to the ductile materials, there is a more elongation. After elongation, the length will be increased, finally fracture will happen. That's what exactly in this we have a different kind of lines. Elastic point, yield point, ultimate point, final fracture point. So for a ductile materials. For a brittle materials, we have a single point, slightly fracture will happen. So always like I'll ask a question, whether in a brittle materials do we have a plasticity? Sorry, do we have a elasticity? In a brittle materials, is there any elasticity inside it? For example, if I apply a load for a brittle or a ductile material well below the yield elastic point, means just the capacity is 100 kgs, I applied 5 kgs. I applied a 5 kgs load, removed it. Whether it may be a elastic material, the brittle materials or a ductile materials, both is in the elastic zone only. There is no change in materials, no change shape or anything. 5 kgs means in the both materials showing elasticity. Only thing is that deformations not visible in brittle materials. Deformation you can't see it. In a brittle materials also there is elastic point. That deformation we won't see it because that material suddenly fractures to the maximum point. These kind of elongations we don't have. That's why we don't have a plastic point and then all other points. Finally, we will have a fracture point in the brittle materials. So, how this particular in terms of atoms, if you see the image, in this what we have done is, we have taken a material, we have taken a small slot to study that. This is the slot what we have taken. We assume like we have 20 atoms, like for example these are 5 outside, 5 into 4, 20 atoms we have taken, and then we applied a load. Once we apply a load, we applied well in the elastic deformation. Means the load is within the elastic deformation. What exactly the atoms are happening is, these atoms of line of atoms, you can see a gap here between these two, this one and this one. Means bond stretching will be done. Between the bonds there is a bonds are joining between the atoms, right? That bonds will stretch within the elastic point, and after that the length is increased here. You can see this one, the length is increased. Means bottom atoms are stretched with their bonds. After that load is removed. This entire load is removed. Again it comes back to the same structure. That's what actually we studied, like elastic limit. Within the elastic limit, when a load is removed, that comes to original structure. Means all the atoms will stretch and then comes to original structure. That is what happened in the elastic point. When it comes to plastic zone, what we have done is, we applied a load to the maximum extent where it changes the permanent shape of it. Means it crosses the elastic point. So here elastic plus plastic zone, what happened here, you can see it, these atoms in a line we have 4 atoms. In the total we have almost 20 atoms. When a load is applied to the maximum of beyond the elastic point, all the atoms stretching is also done. One set of atoms are slipped to the lower level. Means length is increasing. As we have tested in the tensile test, always we will say the length is continuously increasing for a ductile materials. We are not adding a new material. In the side we are not adding a substitute material where it can increase the length. It has to be taken somewhere else to increase their lengths. When it is taking that, particularly whether it may be a thickness or a width, that will be reduced, length will be increased. So in that condition, you can see these particular atoms, the 4 atoms, one atom is slipping to the lower level, the other 2 atoms are slipping to the lower level. Continuously that happens in all the things, and finally we have extra atoms which permanently increases the length. There is a bond stretching as well as atoms slipping to the lower level. After that we release the load. Whatever the bond stretching which is happened between the atoms within the elastic zone, that regains its original structure. So these atoms, between these 2 atoms, whatever the length is stretched, it comes to original structure. So that's why the length is, elastic zone is going back. Whatever plasticity is already happened, means the atom slips to the lower level, that won't come back. That remains permanent. So that's why the final length will remain shape increased, which is already deformed, which won't come back to the original structure. That is called elastic and plastic deformation. So it is permanently deformed in this zone. So there is a permanent deformation. So after this, whenever you apply a load, stretching will be done, already elasticity is happened to the material, more elasticity will be done, and finally fracture will happen in this particular curve. Like this, after this particular zone, whatever the load which we apply, it takes to certain extent, after that fracture will happen. You can see the curve. Basically when you start studying it, when you start drawing the results, what exactly we will write is, in the journal or something, we talk only, okay, we applied a load, the maximum ultimate point is this much, fracture point is this, finally fractured. Okay. We don't see the deep analysis. If you start to do analysis more about the particular tensile only or one characterization only, we can write one PhD thesis on that. But the thing is, we need to know how to write that PhD thesis on that characterization. If I start studying only on this one, this zone, I applied 100, the maximum ultimate point is 100 kgs. I applied 10 kgs, what happened to the material? 20 kgs, what happened? Applied, released. 30 kgs, 40 kgs, 50 kgs, each and every phase, at what point exactly how the material is behaving. And we can change the load application rate, whether it may be at 2 mm per minute or 5 mm per minute. Fast elongation, slow elongation, different conditions we can check. And we can do an analysis, a single material, how deformation will happen with the different conditions. Then on that we can develop a thesis. Okay. And after this point, you can see it, if you draw a line of this, more amount of stress, less amount of strain. After this point, we have a less amount of stress, more amount of strain. Means once it is in a plastics region, the material lost the ability to hold the stress. The next point is, after this point, whatever the material lost their ability to hold the stress. It is continuously straining with a less stress. So if you draw a line here in this point, you can see how much variation it happens before elastic point and after elastic point. How much amount of load it has taken, how much amount of elongation it has happened before and after. So this gives you a clear analysis to understand how the loading conditions happens on a material. So if you draw particular that kind of analysis, that will be a new thing. Because everybody talks about only what is the highest and lowest. If you start saying that how your material after deformation behaving, before deformation it is happening. Before deformation how it is acting, after deformation how it is acting. That particular terms gives you a clear analysis to write a better journal, a better analysis in the characterizations. Next one, this is already have seen it. The next point is fracture happens, material fractured, break. After that we have a curve, a beautiful curve in the system. We'll take it and then we'll put it in the paper and then we'll start analyzing that particular values. Majority of the terms, for example, if somebody asks do some kind of a microstructural analysis or some analysis, then only we'll see the image, what happens to the material. Majority of the times what we do is we'll send the sample to some lab, they will break it, they will give us a graph, we have value, that's it. We never see what happens to the sample, whether that sample, how the fracture happens, whether a cup cone structure is formed for a material, or if it is a polymer or some other material, how the end portions fractured, whether it is a continuous or crossed or which direction fracture happens, which place fracture happens, all those things we don't bother. If you start analyzing those things, then it will give a new break to understand the material in a next level. So you can see it, this is a cup cone structure is formed. So one side we have a cup, other side we have a cone. Two halves are formed, the necking will be done and then finally fracture happens in a ductile materials. If you start studying again, everybody, like for example, it's a time like what we can say, like we can have all constraints, equipment constraints, money constraints, all those things. If even somebody asks in a journal or some other things, we always see, we'll take one sample, we'll take 4 or 5 images, we'll show that. Other end of the sample, we don't take it. When a fracture or a break happens, we need to analyze the two halves of the material, this half and that half, because when you join these two, that is single sample, when it breaks, in the two halves, other sides what happens? This side what happens, that side what happens? For a curve, what is a failure? For a cone, how it is formed? Why in this side only cone formed? Why not in this side? That is which side, whether in the top side or lower side? Cup forming or cone forming, in which direction it is forming, and how much amount of deformation is happening here, and where the fracture starts and where the fracture ends. So all these kind of analysis in a single tensile strength gives you a better PhD, a better output for an understanding. So in this particular thing, To understand it whether it's a ductile or a brittle, basically some studies related to that. One is necking will be formed, a necking will be done, necking will be started. In that particular necking, once the material already stands, like I said, atoms deforms. Atoms will move from one location to another location. When it already crosses the plastic zone, when it enters in the plastic zone, atoms slips to the lower levels. When atoms are slipping, then these kind of cavitations will form. Means atoms are moving from one location to another location. That atom gap called as a cavitation. Cavity formation will be done. Once a few cavities are formed in the material, that cavities will join together and form this kind of crack. Means 4 or 5 cavities are formed together and then adjacent cavities join together and finally form a crack. After the crack, continuously we are applying the load. The material lost their ability to strain more. Stress, don't take the stress more. So it's straining continuously. Then the crack propagation will take place. The crack will propagate and finally a fracture will happen. If it is a ductile, we will see all these kind of behavior. Cavity formations and then crack formation, crack growth, and finally crack breaks into two halves. The material breaks into two halves. This finally analysis we can see it. But if it is a brittle materials, we don't see that. In the brittle materials, directly it will absorb the maximum amount of load. Finally fracture will happen. So we can see that. You can see that one. This is a brittle failure. If there is no deformation and it's a compression load. So you can see that directly once a load is applied, directly a cracks will develop at one point and then fracture will happen. So in this particular ductile materials, we have all these mechanisms like we have cavity formation, cavity growth, and finally crack formation, crack growth, and finally fracture will happen and become a two halves. If you study this particularly compound structure, in which direction cup is forming and which direction cone is forming, and that analysis gives you an idea in how the material is behaving. And for a brittle material, we always see that particular surface on one end. We need to see the other end how it happens. Other end also how the breakage will happen, whether it is a crack formed or how the crack is propagated or it stopped. When it comes to composites, we have a combination of two or more materials. Which material is propagating the crack? Which material is restricting the crack? So what is the material? Like which material is an advantage, disadvantage? That entire studies also will come here. If it is a composite, if it is a single material, then how the failure is happening, how the load distribution is happening in that material. That entire studies will come here. This other thing like as I said, tension, compression, torsion, flexural and shear. So these entire tests, tensile test, will do it in a UTM, universal testing machine. So tensile, compression, flexural, all these we do in the universal testing machine. So this one to illustrate like the surface cross section area and how the elongation will done, how the curves will come. Some animated videos, like you can see the tensile test means applying the load and then specimens are elongating. So necking will be done before that. And you can see this, the polymer testing, load is applying continuously, the length is increasing. You can see the curve is forming here due to stress and strain. And this is a cross section area, whether rectangular or circular, or the cross section. This is a dark bone shape of a specimen. How we prepare, why we prepare a dark bone shape for testing it is, I think probably load, like we can say like load stress concentration point. So the stress concentration point, if it is a uniform specimen, so we can't predict where the stress is happening. So we need to create a specimen such a way that load transformation and a stress concentration to be applied at one point. If we make this surface with the different dimensions, where we have a lesser diameter, that will be the stress concentration point. There the entire load will be applied. In this particular gauge length, the load will be applied and the fracture will happen in this particular area only. You can see it here also. When it is elongated in the center, the failure will happen. This is like if you apply a strain gauges. So how this particular material slowly stretches when you are applying a strain, how much amount of stress is applying and how strain is happening, at which point it breaks the elasticity and it goes to the elastic limit and finally goes to the maximum ultimate point. So when you apply this particular strain gauges, we can see all these points. And there are general mistakes when we are doing some kind of a characterizations. Always when you test a tensile specimen test, 100% we never get same kind of a result. We never get same kind of result two times, because we'll have a material defects, manufacturing defects and testing defects. Majority of the times we'll have a testing defects, because when we are fixing the sample, sometimes we'll fix it correctly, sometimes we'll fix it in a different alignments, sometimes different angles. So these things, if you don't see about that when you are fixing that, then there will be a more chance of getting wrong kind of results. So these alignments are wrong, then automatically the material failure will be in different level. Here I just given an example like for a ductile materials and a composite. The composite having a fibers and this is a ductile material. When a misalignment is happened, then due to the misalignment the entire force is applying here. Because due to misalignment this entire load, more amount of load is applying in this corner. So on that corner stretching is happening, in this corner compression is happening. So the objective of the characterization is to apply a tensile load. But on the specimen, due to the misalignment, what exactly happening is, one end is undergoing stretching, like tension is happening. The other side, this end is going for a compression. So other side is compressing, one end is undergoing tension. So the finally fracture happens, we don't get a clear result, correct value for that, because the same specimen itself acting, one end is a tension, another end is a compression. So that what happens in the bending. Later I will come to the bending part, where we have a bending forces. There we have the top force, where we are bending it, it undergoes some compression. In the bottom portion it undergoes tension. In a single specimen we will have a multiple kind of a behavior. So similar thing it is happening here, where one side it is going for a tension, other side compression. Due to that the failure happens. The same thing if you see for the fibers, the same kind of a behavior, but you can see the curves here. In this we have a different points, elongation and all those things for a ductile materials. For a composite we have a fibers, when a fiber is fractured, whether it may be this side or compression side or tension side, the other entire materials will fracture at a single point. So that's why like the curve is straight and then fracture happens. These entire materials will fracture at one point. So there are many factors which affects the tensile strength. So why particularly among all the characterizations, why have given more stress on the tensile means, as I said, if you want to do a good thesis or good work only on tensile with only single tensile test, so these entire parameters if you consider, if you develop a new material, testing all these, considering all these parameters gives you a bigger analysis, weighing all the parameters, weighing the effects of all the materials and considering all these factor influences, orientation, morphology and then surface conditions and the speed, the loading conditions. So all those parameters, if you do the test, then automatically we can characterize the material in a better level. So these few samples what we tested, one is a Kevlar, one is carbon and then another one is a glass. So you can see all the samples are fractured in the corner level. Our objective is to break this material in the center, but it happens in the lower level. It's not exactly in the center. Means when a tension load is applied, we assume that uniform load is distributed in the materials in the two halves and fracture has to be done in the center. But always we'll see either fracture in the lower corner or the top corner. Then when the fracture is in that corner, we never get an exact result, correct result for the specimen. Because here there is a void or a very defect which is increasing the stress concentration before sending to the center portion. The load has to be sent to the center portion and then in the center, when we combine the top load and the bottom load, the elongation will happen in the center, fracture will happen in the center. But due to voids or defects, this particular fractures always happens here or in the corner portions where we have our fixtures, where we hold the materials. So this is a compression, already I have shown this. this is a 3-point and 4-point bending test. For any specimen, any material, if you develop, there will be a 3-point bending test and 4-point bending test. Bending will be done using a 3 points, or bending will be done with a 4 points. So when we go for a bending, then we'll have a shear force and a bending moments. So basically in the mechanical, what we see more on like shear force, how shear force will affect on it, and then how the bending will be happening, and how what is the bending load, finally the material sustains. So all those things we'll study. What happens if you have a 3-point and you have a 4-point, the load distributions, how it happens, all those things will be there. So this is a small illustration like how to see the 3-point and then 4-point bending test. These terms generally in mechanical we'll see more about it, like changing the loading conditions and then uniform distribute load and a point distribution load and then other loads. We'll study all those things. Every time when we are bending it, we assume that there won't be a shearing of layers. Means when we are bending or breaking it, we assume that there won't be a shearing of layers. There will be a shearing of layers when we are bending it. There is a bending load as well as shear load. That shear will be negligible when we have a more bending. So when we bend more, shearing will be less. When the bending is not there, then we go for a shear. Bending is won't be there means the length of the material to be reduced so that there won't be a bending load. Shearing will be pure shearing will be done. Their bending will be negligible. That's called as interlaminar shear strength. So the dimensions will be less for that particular characterizations. So tomorrow, like I'll continue these characterizations. We have some kind of calculations related to the densities, how the density will be done. Generally, in a density, what exactly we do is we use formula. Density equals to mass by volume. We always calculate by using that formula. Then, but we don't get a real density for it. If we use a mass by volume formula, then if it is a bulk density, it continuously varies. When you compress more, density will vary. So we use Archimedes principle to make it a true density. So what is the true density of a composite? What is the bulk density of a composite? What is the theoretical density of it? And how to calculate the void content. So the void content always reflects the properties of the materials. So that part in the next class, next lecture, I'll explain about that particular terms which are related to densities, void contents, and then some structural properties, XRD, FTS, and which are related to nanomaterials, nanocomposites, and some characterizations related to nanocomposites. If you have a multiple kind of fibers and fillers, so how these interfaces will affect on it, how the research will affect if you have a multiple fillers, fibers as well as nanoparticles. So when you combine on this, how the interfaces will increase, and due to that, how the material properties will vary. Those concepts in the next lecture I'll talk about it. So now I'll start the lecture with this. Our professor now will take over like the tutorial for the next 1 hour.